Okay, hey, we're going to start chapter 4. Chapter 4. Stereochemistry. All right. So about 4 or 5 pages into that chapter, there's a whole bunch of new words for you. Okay. So we're going to just chat, and hopefully we learn all these new words that that the book has laid out for us. So table 4.1, page 113 in my book has stereoisomers, has stereogenic carbon, has stereocenter, has skelmic. Never heard that word before in my life. And then I look and I go, it's not universally accepted. We won't use that word. Racemization, racemic mixture, racemic, racemate, RS configuration, optically active, mirror plane, meso compound, levatory, Fischer projection, enantiomer, diastereomer, dextrorotatory, configuration, chiral center, chiral carbon atom, chiral, asymmetric carbon atom, achiral, and absolute configuration. Do we know any of those words?
Yeah, we will.
You do?
Some of them.
Some of them? That's mirror image. Maybe you knew that one. But at the end, you're going to know all those words, okay? You're going to know all those things. And you're going to know how to apply them and put them into practice and all that sort of stuff, okay? All right. So at the end, we talked about that we need kind of this new system, and that's what we're going to go over today. So we're going to, at some point here, we got to get into the EZ system and the RS system. But kind of before we kick that off, I want to just kind of talk about what stereochemistry is a little bit, okay? So if I have a carbon, because this is organic chemistry, so we're going to have a carbon. Actually, it doesn't have to be a carbon. It can be other things, but it's organic chemistry. So, and I have something different attached to that carbon. I have 4 different things attached to that carbon. It will have a left and a right type image. Okay, so if there's something that has carbon that has 4 things attached to it. So if and here's my bad mirror, okay, but it works. So if this is a mirror going this way, and I'm going to project, so I'm looking into the mirror, and I'm going to project what's into the mirror. How do I do that? So I've got that stays the same, that comes here, that goes over there. So where does my A, B, C, and D go? What do I want here? D and C, okay? So that would be my mirror image. So in your mind, I don't expect everybody to be able to pull this off, but in your mind, are those two structures able to be superimposed? So can you take this molecule and put it over that molecule? And all the atoms would fit over all the atoms. What if I flip it over? If I flip it over, can I put it, if I flip it over, then the B is going the right direction, right? So if I flip it over, so I'm going to do a flip. Okay, so my A is over here now, my B is over here, but then this also flips. Okay. Did that also flip? No. I didn't flip. I messed that up. Now you guys in the peanut gallery, it looks really easy back there. All right. So I just flipped it. So these two are the same because I could flip that again and put it right over that. But can that go on top of that? Can they all superimpose on that?
What do you mean by go on top of? Like, would it be the exact same?
Everything has to match up.
No.
You're saying no?
Yes, I'm saying no.
Okay. Right, so they can't. They can't. So these two structures here would be called some of those words that we read off. First of all, they're non-superimposable mirror images. Non-superimposable mirror images. We also have a stereo center for a carbon. Also have a stereo center for a carbon. And then those two things have a very special name. They're called enantiomers. Okay? They're called enantiomers. All right, so yeah.
So is the enantiomers, is it just the first two, or would that include the flip as well? Like, is it the entire...
The flip is the same molecule.
Okay, so it was just...
I just flipped that molecule over.
Okay.
I-
So it's just the two.
So yeah, if I have to break bonds, so like if I have to take a bond off, rearrange it, and put it back on, then that's very different than just something rotating in space, right?
Got it.
Yeah. All right. So you may know that you deal with a lot of these things in society that you don't necessarily realize. Okay? We'll get these old school ones here. Do I have any lefty people in the room? Anybody left-handed? There's got to be one left-handed person. By in odds, there's got to be one left-handed person. Fake it. Somebody's going to fake being left-handed. No, I don't have to fake it.
Can I?
Are you left-handed?
No.
Is not one person in here is left-handed?
Yeah.
That's not possible. That's not possible. Too bashful.
Natural selection. Use a mouse?
If that Ben, if that's one of your dating criteria, there's really high standards there. Oh man. All right, scissors. A left-handed person has a tough time cutting with scissors because scissors have a non-superimposable mirror image.
I always accidentally use them the wrong way.
Okay? A hammer. A hammer. Can a left-handed person use a hammer just the same as a right-handed person? Is this a left and right-handed hammer?
Yes.
It's a left and right-handed hammer?
So, yes, it's symmetrical.
You're hitting fake.
No way.
It looks the same.
Literally the exact same thing.
Would the mirror image be superimposable? Then it is not an enantiomer. It is not a it does not have it's not a stereo molecule. Okay, it's a stereo structure. Because and think about it, a left-handed person and a right-handed person can use that just the same. Okay? All right, we have the glove already. This is the only glove I could find. because it's winter. It's not winter yet. Somebody told me that earlier. But this is a broken glass glove. So this is the glove you wear if you have to pick up broken glass. But it matters if that's left or right, right? So, right. Yo-yo. A yo-yo. Are there left-handed yo-yos and right-handed yo-yos? Oh, first of all, everybody, this is a yo-yo. Have you ever seen this before? Do you know how these work? All right. Is there a left-handed yo-yo and a right-handed yo-yo? No. Turns out this one is chiral if you count the colors. But if it's the same color on both sides, then it is the mirror image is superimposable. How about a screwdriver? So left-handed screwdriver and a right-handed screwdriver?
No.
So the mirror image is superimposable. How about this bolt? It's a little bent. If it were straight, even if it's a little bent, it's okay. This bolt, does it have a superimposable mirror image? Yes or no? Okay, we're going to go by hands because I'm seeing. So if you think that this bolt has an enantiomer, a non-superimposable mirror image, raise your hand. I got 3 or 4 over here. I got no one over here. You didn't see the bolt. Is the bolt an enantiomer?
So if it can be used
If it's
both
straight.
ways, it is not.
If it has a non-superimposable mirror image, it's an enantiomer. So would the mirror image be superimposable?
No.
Why? Why do you think? The threading. Righty-tighty, lefty-loosey. It has handedness. Okay? Righty-tighty, lefty-loosey. The spiral on that bolt has a non-superimposable mirror image. I could have a left-handed bolt that would have the opposite threading, and it is lefty-tighty, righty-loosey. Those things happen. All right, so we're going to do a little experiment now. Do a little experiment.
Have vanilla and soy sauce.
I
No.
really don't.
Okay, so we're going to pass these around. You're going to have the big bottle and have the little bottle, okay? And you're just going to, don't take like a super big, it won't kill you. May not even damage you. But take a whiff, okay? Smell what they smell like, all right? And I'll pass, and we want everyone to take a little whiff. And then don't say what you smell, okay? Because you don't want to influence your neighbor. Don't say what you smell.
Is this the some people's
Just put it in your brain, okay, of what you think it is.
When we're doing all the smells, like, do you want a specific scent, or do you want do you want to get super in detail, the most detail we can to put the name of the scent, or are we trying to figure out the broad smell?
I'm trying to figure out the underlying chemical compounds. He's expecting a
We're gonna start this one over here, and we're gonna start this one over here, and we'll find out what happens. Okay? We're gonna run an experiment. So take the cap off. If you spill them, it's okay, but please not spill them. Here, I'll take the cap, and you can just pass it around. Yeah, I'd like for you to give me the molecular formula.
I got it. Smell like the molecular. Not.
Yes.
I know that.
4 different things attached to a carbon.
Do you guys know what hard water is?
4 different things.
I looked it up. Pass it down this way.
Go that way with it.
Do you think that
Where in the world did you go to lunch that they give you a box like that?
That sounds fun, doesn't it?
Ah, okay. All right, keep it moving, guys. Keep it moving. Are you?
Is it the same thing?
We're running the experiment.
Fine wine,
Yeah, we'll bring it up to the front. Thank you. Okay, here you go. We'll go that way with it. Come on, guys. It's only a 55-minute class. Ben, what's the structure?
What's the structure?
Yeah.
What I just smelled?
Yeah.
in from my head. That's too specific.
Are they?
I doubt other people will agree with me or what. Apparently we don't know how to smell. I mean, take a deep breath in.
I see it.
The other one has a different.
Are these stereo?
What? Let's go, let's go, let's go. It's a good Friday activity, I suppose.
That's very. Yeah.
Everybody's very tired. At least I am.
Everybody's tired.
It's Friday at 1.
Did you get to sniff the little bottle?
Yeah, sure.
The red one? The red cap?
The little one.
Yeah.
Yeah.
Okay, pass it along. No, don't say. Just put it in your head.
Same with the scent, so just know that it's relaxing.
Oh, you like it. It's like aromatherapy.
It's kind of cleansing.
Okay, did the little bottle make it all the way up here?
It's still got back.
Hold on. I couldn't smell the little bottle.
You burned your.
Yeah.
Goodbye.
Okay. So, did everyone get to smell this guy? You all got to smell this? Everybody got to smell this one? Okay. Where's the little bottle? Okay. Does everybody get to smell that one? Am I recording? Yeah, it looks like I think I'm recording. Yeah. So you got the little one back here? Okay, everybody got to smell this one? Everybody? Okay, so what's the little bottle?
Black.
You think it smells like black licorice? Okay. Anybody else? Dill. A little bit of dill.
Yeah. Spearmint.
And the little one?
The little one smelled like spearmint?
I thought they smelled the same.
They smell the same.
It smelled the same?
Never smelled that to me.
I thought they did.
It smells like a black pipe.
Well, I feel like they all that's what it is. I don't necessarily think that's what it is. It's from my right now. And I'm not a huge fan of my I love black liquor. It looks like Okay, you fit in like a Scandinavian equally well. Like that's it's like
I couldn't tell you off the top of my head.
Okay. So we're a little confused on what the little guy smells like, right? What about the big guy? Everybody goes with spearmint. Toothpaste, okay? Spearmint? Peppermint-ish? Okay. So, I think I have the structure right. Pretty close, at least. You won't know if I'm wrong, so. So, here are the two structures, okay? One is plus carbone, and the other one is minus carbone, okay? One is S plus carbone. Oh, and I could name it. Well, I don't know. I could look this up. S plus carbone. And the other one is R minus carbone. Okay? So, are these molecules...
You're missing a thing.
Where at? Right here? Okay, that's what I thought. It's cyclohexane, but still, it's good. Cyclohexane ring?
Well, wouldn't it be Ene now?
Ene now, yeah. Not a benzene. Okay, so we're just having a little side conversation up here. So are those superimposable mirror images? Are they mirror images? Yes, they are. Actually, well, I might have flipped it around, but if I take this molecule, I'm going to go this way with it. So I'm going to draw the mirror image here, okay? And then if I flip that molecule over, if I flip this molecule over, which one is it? Is it this one or is it this one?
It's the second one.
It's the second one.
It's the second one. So if you take this one's mirror image and you flip it over, it superimposes on this. So this is the mirror image of that one. Okay? That is the mirror image flipped over. Okay? So they are what? Non-superimposable mirror images, right? Non-superimposable, right? Because they're non-superimposable mirror images. These two things in these two bottles are non-superimposable mirror images. So they are what? They're enantiomers. Okay? What carbon up here has 4 different things attached to it? Which one?
Nice.
That one? But it looks like it has the same thing attached, right? Well, here's where the RS thing comes into, and we'll talk about what that is. But there's a priority that's given, and so the way in which you count around that determines if they're different or not. Yeah.
So can you explain why on the mirror image on the very left, how come that has the double bond on the bottom on the right instead of the left?
Oh, it doesn't matter, but still.
Oh, it doesn't matter.
There we go.
Okay.
Good question. Good. This is right, but this has free rotation too.
Makes sense. So it
But-
doesn't really matter, but okay.
It did matter in my drawing.
Gotcha.
Okay. Another question? Another call out. No, okay. All right. Sorry. All right. Maybe. All right. So, why is it that everyone said that one of them is spearmint and the other people thought that it was something different? Because enantiomers have the exact same physical properties. These are going to have the same boiling point. They're going to have the same, if you could, melting point. They're going to have the same spectra. They're going to have, everything's going to be exactly the same. All the physical properties are the same. So how is it that you smelt them different? Huh? They have different stereochemistry, but why did you smell them different?
Binds differently to your
Genetics.
Okay, why? Well, no, this is more of a learn. Well, maybe if you couldn't determine the difference between the two, if the two smelt the same, raise your hand if the two smelt exactly the same. Yeah, your genetics are messed up, so that's genetics. All right? But how do you smell?
It's a chemoreceptor, so it has to bind.
There's a binding site in your nose, right? It's an olfactory receptor. And what is that binding site made out of? Proteins. And what are proteins made out of? Amino acids. And are amino acids, do amino acids have stereochemistry? Do they have L? Do you say L and R amino acid?
Yes, you do.
Yes, every amino acid has stereochemistry. It might be one that does not, of the 20 natural. Okay? So each naturally occurring amino acid is a stereoisomer. You are built up with all one stereoisomer of amino acids. Okay? You're all built up with the L amino acid and all the different proteins that you have. So your nose, okay, here's the thing. Here we go. Your nose is chiral. You have a chiral nose. Okay? Like your nose has a left and a right hand to it. Not each nostril, but okay? So your nose is chiral. It has a left and a right-handedness to it. So this one filled one receptor. And so you knew what this one was because you were in the car when you were 5 and you're driving down the road and you said, "Mom, what's that smell?" And they were going through a spearmint field or they were harvesting spearmint and they said, "Oh, that's spearmint." Okay? You probably haven't smelled this one because these are caraway seeds. So there used to be, so it's a spice and you cook with it, but there used to be buns that had caraway seeds on them. They're not popular anymore, but they were popular way back in the day. And so no one knows what this stuff is anymore, but it does smell a little bit like black licorice. And some people said it smelled like something else. What was it? Dill, like a dill, and it's like a dill seed. Okay? All right. One more thing about chirality. Bryce, I noticed you are sporting a pretty good pair of sunglasses. What kind of sunglasses are those? Are they real Ray-Bans or are they like knockoffs that, China put the tag on the side? Now I got to steal them. They're the real thing. Okay, so what's interesting is usually college students don't have nice sunglasses. For whatever reason, it usually doesn't happen. Later in life, I became a fan of good sunglasses because I never lose them, and they're better. So these are prescription, so you don't want to put these on, but these are Maui Jims. And if you've ever had a pair of Maui Jims, you'll never want another pair of sunglasses. So these are my prescription ones. I drive with them. Okay, they're nice. These are non-prescription. But, I like these too. So the interesting thing about these and Bryce's Ray-Bans back there is they're polarized. What does polarized mean?
Hey, we talked about this. Oh, yeah. In honors. Yeah. I should remember it.
Wait, I remember.
Who was your honors teacher?
Dr. Lawrence.
Of course. So Bryce, does anyone else have polarized sunglasses? A few people. So when you have your polarized sunglasses on, and sometimes if you look over at your window, do you see that it's like dark sometimes?
It's got like weird things.
Weird things to it. Have you ever looked down at your like control panel and it's like dark, really dark? Does that ever happen? Not like because you have your sunglasses on, but it's like dark, blacked out. Bryce, does that ever happen? Yeah, sorta. So if I take these two pairs of sunglasses, and I can see through both pairs now, I can see all of you very well. Okay, and I rotate one of them, it starts getting dark, and then right there, it's completely black. Okay, so I'll let someone try if you want to try that, or try Bryce. I tell you what, you take this pair and see if that works. You put yours on, see if that works with yours, because I believe they're polarized. I mean, they've got to be the Ray-Bans. We'll find out.
You don't remember that? We were talking about 3D glasses and then talking about floating.
Oh man, they look better on you, I think.
Yeah, that's right. So you're gonna need this.
Does it go dark?
Pretty dark.
And then if you rotate them back around, you can see through them again?
Yeah.
Okay. Polarized sunglasses, all right?
Are you saying that the left and the right lens?
Yes. How does that work, though? How does that work with chirality? You're saying that has something to do with chirality, right? Yes.
Go ahead.
Go for it? Or you have a question? Okay. So, everyone thinks that light looks like, when we draw a light on the board, we always draw it like that, right? Oh, here's a wavelength of light. Actually, light is a corkscrew. Because it's in all three directions. It's in all 360 directions all at the same time. So it's actually a corkscrew. Okay? And so if you want to really, light has every sort of vector associated with it. Okay? All those vectors. And in light, you have a left-handed and a right-handed corkscrew, okay, coming from the sun. And so what a polarizer lens does is it blocks out, it filters out every wavelength except for the one in the plane of the polarizer. So it takes that corkscrew wavelength and it just takes the one wavelength that does make it linear. Okay? It's kind of hard to imagine, but so that for whatever reason, I'm not sure, clears up glare, and you can see a little bit better, and this, that, and the other, less reflections or something. So then, if I do the other one the same way, I have another polarizer, but I polarize it this way. Well, then my vector is the other way. So I can see 100% through those two. No, hold on. I can see 100% as long as those two vectors aren't lined up. But when those two vectors line up, then it goes to 0. They filter each other out. Or it's the other way around. But when you line those, get them in the right alignment, it goes to 0. Okay. So there's chirality to light as well. And you can use the chirality of light to determine this number, this plus and minus. So you put a chiral molecule into what we call a polarimeter, a detector, and it uses plain polarized light instead of just regular visible light. It runs it through a plain polarizer. And so then the molecule will rotate light a certain direction, left or right. And it's a physical property just like a melting point. So you can't say that S is always going to be plus and R is going to be minus or anything around. It's the same as trying to predict what a physical property is. You can't really do it. You have to run the experiment and find out if it rotates light, positive or negative. But two enantiomers will always rotate light the exact same amount in the opposite direction. Yes?
How can you look at that and say this one's X and this one's Y?
Yeah. We're going to get there.
Okay.
I just wrote down what was on the bottle. I just wrote down what was on the bottle. It says R minus, right? R, you're going to verify R minus carbone. So that I just wrote down was on the bottle. Okay. All right. Kind of get the idea of stereochemistry. It's, I don't think many biologists really pay attention to it a whole lot because it's just kind of like always there. But every protein, DNA, those two macromolecules are all chiral. Many of the biomolecules that you'll deal with are made enzymatically, and so then they are going to be chiral. You go inside, you're a chiral creature. Okay. All right. So, RNS. Let's figure it out. Let's figure out which ones, if I've labeled them right. I should have maybe paid better attention or looked at my notes or something. But RS. So the way it works is, we'll just start here. We're going to give groups a priority. Okay? And the priority is based on its atomic number. Okay? So what has the lowest atomic number? Hydrogen. So hydrogen here, the hydrogen is always going to be given the lowest priority. So if this were a uranium, it would be a really high priority because uranium's really big, okay? But it's hydrogen. So hydrogen always gets the lowest priority. And then we have this ranking system, and we go through and we give everything a rank. And then, here, let's do it. So how do you want to rank this? You want to rank A as high or A as low? We're going to go low, and we're going to go D as high. Okay? We good with that? We're going to go A is low and D is high. Okay? Then what you want to do is kind of like our Newman projection. You want to put the hydrogen going behind you, going into the other room. So in this case, what I have to do is kind of put my eye over here. Okay, if I put my eye, this is an eye, a very bad eye. If I put my eye over here, then I'm looking, and the A is going away from me. Okay, and so if I were to draw this with three things here, oops, I'm going to draw them this way. It's going away. Yeah, I could do that. So remember, the D is coming into the room and the C is going that way, so is going in the other way. So what if I put the B here, then I'm going to put the D here and the C here. Is that right? The opposite.
You have two of them. You just have the B and the D up top and bottom.
Well, here. Let's do it with a model. You got your model kit back there? guys asked the question, how do you do the... We'll fix these sticks here.
Swap one of the orange ones with one of the purple ones. Swap the orange and purple. So that they have this word at the same time.
All right, let's see what I got here. So we're going to go with... all right, so what we're going to go with here is A is... Remember this, you guys follow this. A is red, okay? B is black. I gotta remember my colors. I haven't had to remember colors in a while. This is D, and this is C.
Didn't you say A was red?
D is red, A is white, B
Sorry.
is black.
It's this.
Okay. Okay, we're good.
My kids are so old. I have not taught colors in a long time. All right, so D is red, okay? C is green, okay? And B is this black one. So I need to go like this. So where is D is where?
Red. So you need to look through the C, which is green to the center.
You know, look from green to
Yeah, green to the middle.
green to the middle.
So it should be.
I got it backwards. Hold on.
You need to look through the C, which is the green. So look at C.
There's just nothing to put on the front one.
So this is C. Yeah.
No, that's.
Which one is
It
this?
should be A,
Is this
B,
D?
and D.
No, I won't do that to you.
It should be A, B, and D. So A would be on the bottom.
No, A is going back. A goes back.
C is on the bottom.
He's on the bottom. He's on the bottom.
Yes.
So A goes back because I take A, I got to make it go back. My problem is I'm looking the wrong way, so I turned it the wrong way. So A is like that. This is my B. This is D, right? So I'm going to look this way. Boom, right there.
Oh,
There you go.
that was good.
Okay? Right there.
Okay.
So that's that. And then I'm going to look like that. Okay? Because the A goes back. So now, D is high priority, right? C is next. And now this is and of these three, this is the lowest next, right?
Lowest. Just randomly assigned.
Well, we did A is low.
So it goes from.
So D has to be high because we don't want to do that. So then my rotation here is from high to next to lowest. So my rotation is that way. Is that clockwise or counterclockwise? So it is S.
But S is not always negative.
That is a physical property. This is a physical property. This is, I put it in the machine, I shine light through it, and I look which way polarized light is moved. It's moved to the left or moved to the right. This is absolute. This is absolute stereochemistry because I'm going to assign a name to it that says you have this progression from highest to lowest. Okay? All right, so if I were to then do this one, okay, I'm going to do this one. I'm going to break this bond because I got to make the mirror image.
No,
So, hold on, what happened here? D was what? D was green?
No, D is green, D is red, B is black.
D is what color?
D is
Over here. D was red? Oh, okay. Remember, you got to remember this. Okay. So if I look at this one, if I do this one, it should be exactly opposite. Okay, so if I look at this one and I put that behind it, now my progression is clockwise.
So D. Okay, say that again.
So here's this molecule, okay? And if I take it and I put the hydrogen going back like that, now my progression is to the right from green to red to black. Goes clockwise.
Because you always count from low to high.
Always count high to low.
Oh, you started at A, so then it got.
Oh, I put A behind. A goes behind because it's the lowest. You don't even count it.
Oh, okay.
It goes. You put it behind.
And so you started at D, C, B.
D, C, B. D, C, B. And now this progression is right. Like there's like the entire peanut gallery sat on that side of the room. There's I got no comments except for Zach here. Just one comment up here.
We're just low key about.
It's like your two classrooms. All right. I'm gonna have to assign seats, kind of mix you guys up.
Let's not do that.
I don't know.
All right. All right. So now let's do it. Just do one harder. Yeah.
Would you mind drawing the projection like you did for the first one?
So this was green. Should have had more colors. Did I get that right? Was D green? Was D green before?
Yeah, no, it was red before.
He was red.
It's okay, we can, it doesn't matter to me.
You can
Oh,
adapt to
Christmas,
change.
it's okay.
Yeah.
That's Christmas, like I literally.
It's still Christmas.
All right. Okay. So now let's do this one. Let's do this. So I had a different color somewhere. Where'd it go? No, I did not, huh? Oh, it is way down there. Okay. So let's figure out if this is R or if that's S. So now you know where R and S comes from. Okay. So here things get a little bit more complex. First of all, let's look at this carbon. That's the chiral center. Got to have 4 different things attached to it. So what's going to be the lowest one? Okay, that's going to be lowest, right? Now we're going to look to see which has. Remember, we're going off of atomic number. Okay. Going off of atomic number. So we'll go here. What's the atomic number of that atom? 6. What's the atomic number of that atom? 6. What's the atomic number of that atom? 6. So it's a 3-way tie. It's a 3-way tie. Okay? So then you have to go one past that. Okay? So I'm going to go down here. So if I come down here to this carbon, then if I go out one more, I have another carbon, right? So if I come to this carbon and I go out one more, I have another carbon. Okay? If I come down to this carbon and I go out one more, I've got another carbon, right? If I come to this carbon and I go out one more, I've got a hydrogen. So this carbon beats that hydrogen. So this group beats that group. Okay? Well, just to tell you how this is going to work, this group's going to beat that group too. Okay? Because it's got two hydrogens.
Same thing.
Same one. So this is going to be my highest. Yes?
Is there a reason you went to the hydrogen instead of a different carbon?
I did go to carbon first. I went carbon,
Yes.
and then I...
From your rightmost carbon up to the right.
So, okay, let's do it again, and I'll show you. Let's do it. Ben, look up here. You'll get it. Okay, I see it. So we're going to do it again. Carbon, carbon. Okay? So that's a tie. So now then I'm going to go carbon, and now this one goes carbon. Now I come back to the same carbon. This is carbon, this is hydrogen. I can't go back to the same carbon again. So that carbon beats this hydrogen.
And we didn't go back to the center one because
We're already we're comparing this, who's going to win on these two, because we're one carbon away from the stereo center. Because all three of these tied. So we're going to look one carbon away from the stereo center. Okay? Let's go to the next one, then maybe it'll make some sense. So this is the highest. So now we have to determine which one wins, this one or this one. Okay? Well, they're both CH2, so we got to go to the next carbon. We got to go to the next carbon. So we got to say, if I go here and I go here, I got a carbon, right?
It's the one on the left.
So then if I go here, I got a carbon. But if I go here, I got an oxygen. And why does oxygen win? Because it's 8. Because it's 8. So then this one is the next. Well, this one. Okay, so that's the next. Jason, if I were smarter, I would have started with the other structure. Okay, so my progression then is I got to put the hydrogen back. The hydrogen straight forward at me. Ugh, that's why I just said that. But my progression is, this is the lowest, so this is priority 4, okay? And then this one's priority 3, this one's priority 2, and this is priority 1. Okay? So 1 has highest priority, 4 has least priority. We'll just go with that, okay? So then, okay, I'm going to show you a trick. I'm going to show you a trick, and then when you get stuck like this on sapling, you'll know what to do. Okay? I showed a trick. I should show you my trick about balancing equations. I showed that earlier today, and it didn't get a big wow. But it should have. So this one should get you a big wow. I got to get one wow today. Yeah.
I just have a really quick question. Can you explain how come the one that you have labeled 1 is the highest instead of the one with the oxygen? Because doesn't oxygen have a higher atomic number?
Right, but I didn't make it all the way up to oxygen when I was checking to see if it won. I only made it to hydrogen, and this one has an extra carbon. So I never made it up there to go like that. You always just go to the next one. Just go to that's where you're gonna make a mistake.
Okay.
Go to the next carbon and then do the thing to see who wins.
So it's all related to the orange dot that you have. That one.
And what is the orange dot?
Okay.
And what is the orange dot?
Center.
Yes.
There we go. Okay, that makes sense.
Okay? All right. Here's the trick. Here's the trick. Forget that the hydrogen is coming forward. You want the hydrogen to go back because it's 4. It's the least. You want it to go back. Just forget about it. Just say, it's coming right at me, but I'm going to pretend that it's going back. Okay? It's coming right at me. And my progression here is 1 to 2 to 3 is what? Clockwise or counterclockwise? Clockwise, right? So then I have to remember, oh, wait, the hydrogen is coming right at me, and the hydrogen really needs to be going away from me. So it's opposite.
What?
So this one is S.
What?
You got to stick with me. It's like, All right? So here we go. We're going to go 1, 2, 3, 4. So the hydrogen's coming towards you, right?
Yes.
Where should the hydrogen be going in order to do this? Away, right? But it's coming towards me, and I don't want to try to rewrite it and try to get my head into computer science in more ways than one. But I don't want to go back behind the board and look, okay? So, but my progression is R, right? But the hydrogen's not going back. It's coming forward. So you flip it to S.
Okay. I think I get it. I don't know.
Let's do this. Well, we're out of time.
Can you just say the last 6 words you said?
So the progression is clockwise, right? But the hydrogen is not going back. It's coming forward. So you say it. So instead of it being R, it's S.
I think
Let's do this one.
I think I understand.
This is still my number 2 group, right? This is still my number 2 group. This is still my number 1 group. And this is my number 3 group, right? But in this case, hydrogen is going back.
So it stays the same.
So I go from 1 to 2 to 3. That's R, right? I don't flip that one because the hydrogen's going back.
That makes sense. It makes sense.
Yeah.
It's like you know what you're doing.
Can you say that louder? Can you say that louder?
It's like you know what you're doing.
I'm gonna put that on there.